Welcome to Spring LIB.
Okay, we have a couple alkenes and some reagents. We need to determine what the products of those reactions will give us. First, we have Br2 in water. And recall that what this will do is install a bromine and an alcohol that are they are anti to each other with respect to the bond of the carbons that they're bound to, respectively. And that the alcohol will end up on the more substituted side of the double bond. That is, one substituent will end up here and one will end up here. And since this is the more substituted side, that's the side that will get the alcohol. So we can simply redraw the substrate without the double bond, put a bromine on one side and an alcohol on the other. And, oops, did that backwards. Bromine goes on the less substituted side, alcohol on the more substituted side. Notice that there, in fact, are no stereocenters in this molecule, right? This carbon has two ethyl groups off of it, and so it doesn't have four unique substituents. And this carbon has two hydrogens coming off of it, which means there are no stereocenters on that carbon. So, in fact, this product is simply drawn not with wedges and dashes, but like so, which is why it's necessary for this problem, because they say if you incorrectly show stereochemistry where none exists, you may lose points. No stereochemistry exists on this molecule, so we should not show stereochemistry in our products. Okay, next. We have BH3 in THF first, and then hydrogen peroxide, water with sodium hydroxide. This is hydroboration oxidation. And if you recall, what hydroboration oxidation does is it installs an alcohol on the least substituted side of the double bond, right? Anti-Markovnikov, which is, not easy to do. And it also installs hydrogen on the other side of that double bond, and that those two substituents are cis to each other. So I'll redraw the substrate without the double bond. I will say, okay, let's install an alcohol on the terminal carbon and a hydrogen that is cis to that alcohol. And notice once again that there are no stereocenters in this molecule, right? We've got two ethyl groups on this carbon, so it doesn't have four unique substituents, and we've got two hydrogens on this carbon, so it does not have four unique substituents. Therefore, neither position is a stereocenter, meaning we simply have this alcohol, and in fact, we don't even have to show this hydrogen. Okay, last one. We have a cyclohexene with two methyl groups on adjacent carbons, and we are reacting this with H2 with palladium over carbon. Now, if you recall, this will turn double bonds into single bonds, but specifically it will install two hydrogens that are cis to each other. Therefore, we can redraw this substrate without the double bond and draw the methyl groups in, and then draw cis hydrogens. Now note that these are, in fact, stereocenters, and so it is correct to show wedges to hydrogen. And if we wanted to be more thorough, while this is a perfectly fine representation of stereochemistry, the more common sort of representation that we might see would be using wedges and hashes, not three bonds in the plane and hashes, although that is valid. So it might be something like show hashes to the methyl groups and wedges to the hydrogen, like so.